Hi there, you're in the lab with your mate JJ. Today is Old Book Teardown Day. We're going to be tearing down an old book. Silly job title for today is Phase Pharaoh. Today I'm the Phase Pharaoh. The book we'll be tearing down is Semiconductor Reference and Application Handbook, published by Archer in 1978. So this is like a it's like a product list of semiconductor devices that were available in 1978. It brags on the front here. It says includes over 46,000 semiconductor substitutions. So I'm not exactly sure what that means. Maybe we'll figure it out when we have a look in this book. It's not a big book. I picked it because it's small, and I'm running out of time to get this video published. So we're just going to do a small little one today, and that's this one. So let's pop over to the bench and have a look at what's inside. All right, well, here we are on the bench, and this is our book, published by Archer, catalogue number 2764002, for sale for $1.95. Semiconductor Reference and Application Handbook. Includes over 46,000 semiconductor substitutions. We've got auto circuits, logic circuits or amplifiers, and we've got 7-segment displays. Wonderful. On the back, so this is Radio Shack, which is a division of Tandy Corporation based in Fort Worth, Texas, and in Canada, in Ontario. And in Australia, they were known as Tandy. They weren't known as Radio Shack in Australia. They were just known as Tandy, and they were in Rydalmere in New South Wales, near where I grew up. Well, I grew up in New South Wales, near Rydalmere. Not that close. And they're in Belgium, and they're in the UK. Otherwise, there's not much on the back. So, let's see what we're dealing with. So, integrated circuit cross-reference by generic and catalog number. Okay. So, we've got generic numbers like 21L0 or 74C00. All right. And here's our standard. Yes, okay. So I remember some of the 4000 series semiconductors. I forget which way around it was. One of them was CMOS, and one of them was TTL. Maybe it'll tell us about that in this book. We'll see. Okay, so they've got them sorted by generic name, and then they've got them sorted by catalog number. So it must be that that these are the catalog number parts at Radio Shack, presumably for all of Tandy Corporation, which was global. All right. Anyway, it's got an introduction. It's got a section on how to use this book, so that's going to be helpful. We've got care and handling of transistors, silicon or germanium operating considerations, silicon versus selenium rectifiers, soldering precautions, about case dimensions, general precautions, testing a transistor. It's actually something I need to do at the moment, is I need to test some MOSFETs, which don't seem to be working. I'll be back in a tick. All right, and then after testing transistors, we've got handling of integrated circuits, diodes and rectifiers, general purpose diodes, Zener diodes, bridge rectifiers, transistors, bipolar, field effect, unijunction, display and optoelectronic devices, cadmium sulfide photocell, also known as the CDS cell, clock display board, clock module, LASCR. Okay, I'm not sure if that's a silicon controlled rectifier. It might be, I don't know. LED, phototransistor, selenium solar cell, silicon solar cell. Integrated circuits, CMOS, linear, memory, microprocessor, and TTL. There we go. So we'll learn about that. And then we've got special purpose devices. We've got the diac and the SCR and the triac. Then there's important suggestions on the use and replacement of transistors. Okay. And then we've got cross-reference / substitution listing. And then we've got cross-reference listings. We've got case styles. We've got symbols. And we've got a glossary of words, symbols, and abbreviations. And then there's what they call Radio Shack experimenters accessories. Fair enough. This is from 1978. Fort Worth, Texas. All right. Look how yellow the pages are. I suppose whoever owned it was a smoker. So what have we got? Introduction. This semiconductor reference, this semiconductor reference handbook is intended to be just that, a reference handbook. It is not a definitive text on semiconductors. It is a compilation of data on Radio Shack's line of prime quality Archer semiconductors. Oh, I see. So Archer semiconductors are a brand of Radio Shacks. I thought they were the publisher. So I guess Radio Shack's the publisher. Every Archer device covered in this handbook is guaranteed prime. They are not fallouts or seconds. All are top quality with known JEDEC, EIA, or manufacturer's numbers. At the back of the book is a cross-reference listing for replacement of transistors, diodes, and other interchangeable semiconductor devices. The total number of cross-reference devices exceeds 46,000. These cross-reference / replacement listings are computer selected and are based on careful analysis of important parameters of the listed devices. Note, if you can't find a replacement listing for a device you require, refer to the specification listings of the appropriate Archer family device. Often you will be able to make suitable replacements based on the information presented. Each Archer replacement should meet or exceed the required parameters. However, due to differences in quality control and manufacturing procedures, which often allow for or result in broad parameter variations, and because many of the Archer devices are capable of better performance than the original, Radio Shack does not guarantee, nor does it imply, that the listed items will provide an exact replacement in every instance. Therefore, we recommend that you check the voltage and current requirements of the circuit and other pertinent specifications before replacement and compare with the specifications listed for that particular Archer device. Okay, so sounds like this book is Radio Shack pimping out their Archer line of semiconductors. Fair enough. How to use this book. This book has been prepared to aid in both replacement and original applications of semiconductor devices. They mean semiconductor devices. Anyway, the information included will be invaluable for the service technician as well as the circuit designer, whether he be an engineer, hobbyist, student, or electronics experimenter. We have included hints on handling semiconductor devices, operating considerations, and some simple tests to aid you in evaluating the quality of the device and existing equipment, and thus the need for replacement. Also, a complete section on the specification for each of the Archer devices is included. If there is any question in your mind about replacement, equivalent, or original use, refer to the appropriate category in the book. You will find the important characteristics specified there. The next to last section is an extensive listing of replacement and cross-reference between other manufacturers' numbers, both JEDEC, EIA, 2N numbers, and in-house designations, and the Archer devices. This listing provides for the substitution of over 46,000 semiconductors with Archer devices. The final selection includes case-style drawings and some handy reference notes, a comprehensive glossary of commonly used words, plus symbols and abbreviations. Care and handling of transistors. Most modern transistors are somewhat immune from mechanical shock. However, it is always a good idea to keep them from excessive mechanical shocks, especially the metal case type. Avoid dropping, etc. When cutting transistor leads, use scissor-type cutting tools rather than diagonal cutting tools, which use a crimping action. Crimp-type cutting tools produce a mechanical shock along the lead, which when transmitted to the semiconductor chip or metal can cause fracture. Consider the force with which the lead flies off. Consider the force with which the cut lead flies off the crimp-type cutting tool, and you have a good idea of the intensity of the equal and opposite force which acts on the lead going into the device. It is always a good practice to use a heat sink tool on a transistor lead when soldering. Use low wattage iron, 30 watts or less. Heat from soldering can cause problems, especially with certain types of semiconductor devices. Thus, to be sure, always use a heat sink on the lead when soldering. Gripping the lead with long nose pliers between the solder connection and the case of the device makes a good heat sink, or use a tool designed for such use. Silicon or germanium. The quickest way to determine if a transistor is germanium or silicon type is to check the normal emitter base voltage drop. With NPN devices, if the base is approximately 0.25 volts positive with respect to the emitter, it is a germanium type. If the voltage is about 0.65 volts, it is a silicon type. For PNP devices, the voltage will be the same value but opposite in polarity. 0.25 volts for germanium and 0.65 for silicon. That hasn't changed. That's still true, I believe. Operating considerations. Before replacing an original equipment device with the recommended Archer type, A. Compare the lead or terminal arrangement of the Archer replacement device with the lead or terminal with the lead or terminal arrangement of the original device. If these arrangements are different and the original transistor is a plug-in type, bend the leads of the Archer device so that the base emitter and collector leads will mate with the original transistor leads. Trim the leads after soldering in place. Caution: be particularly careful about pin circle and inline lead breakout type transistors. Often one manufacturer makes a type with inline leads, while another make the same type with pin circle configuration. Double check both the original and the replacement device before soldering or plugging in transistors. So here's a bottom view of the pin circle and the inline. I don't know if you see many pin circle ones these days. I'm not sure. All right, B. This is a list, some sort of a list. What list are we going through? Before replacing an original equipment device with the recommended Archer type, A, check the leads, and B, Certain considerations are involved whenever an original equipment transistor is replaced by having a different type designation. When an Archer series transistor is used to replace an original equipment device in an untuned amplifier stage operating at a low signal level, such as the untuned RF amplifier antenna stage of a radio receiver, or a low-level AF amplifier stage, it is generally unnecessary to make any circuit adjustment to assure proper performance of the equipment. However, when a replacement is made in a tuned RF amplifier stage, it is always advisable to check the alignment of the associated tuned circuits to assure proper tracking and to achieve the required gain without loss of stability. C. When replacements are made in stages operating at relatively high power levels, such as Class A and Class B, AF output stages of automobile radio receivers, phonographs, and AF amplifier systems, the transistor bias should be checked and adjusted, if necessary, to protect the Archer replacement transistors against excessive dissipation and to minimize distortion. Means for making adjustments are generally provided in the equipment, and the necessary instructions are usually given in the equipment manufacturer's service data. D. When installing an Archer transistor as a substitute for an original equipment type in an FM tuner, TV tuner, or other circuits operating at frequencies in the VHF or UHF regions, it is extremely important not to change any of the lead lengths or position of the original circuit. Before removing the original transistor, carefully note its position with respect to other circuit components, as well as the length and placement of the transistor leads, and duplicate these details as closely as possible with the Archer replacement transistor. Failure to observe this precaution can result in improper tuning or circuit instability. The same holds true for any replacement of integrated circuits, especially in FM radios and TV receivers. Failure to observe this precaution can result in damage to the device. Transistor substitution in tuned circuits will often require realignment of the circuit. Silicon versus selenium rectifiers. Silicon rectifiers are inherently more efficient than selenium or other metallic oxide type rectifiers. When a silicon rectifier is used to replace a selenium rectifier in the power supply of a typical line-operated radio or TV receiver, the silicon rectifier will frequently deliver higher DC output voltage than the original device. In some cases, this higher supply voltage may improve the performance of the equipment. However, in many other cases, it may immediately or eventually damage filter capacitors and or other components which were designed to withstand only the voltage delivered by the original selenium rectifier. To prevent such damage, it is generally advisable to insert a power type resistor in series with the silicon rectifier, either on the output side between the AC supply and the rectifier, or on the output side between the rectifier and the first filter capacitor. The value of this resistor will depend on the required reduction in the DC output voltage and on the DC load current of the equipment. This value may be determined experimentally or calculated from the equation R equals E over I, where R is the required resistance in ohms, E is the required reduction in DC output voltage in volts, and I is the DC load current in amperes. The wattage rating of the resistor should be at least 2 times EI, in no case less than 10 watts. Soldering precautions. Extreme care should always be used in making solder connections to semiconductors. Momentary application of excessive heat or even prolonged application of a properly heated soldering tool to a semiconductor lead or terminal can permanently damage the device. Observe the following precautions in soldering a semiconductor lead or terminal. 1. Solder as far as possible from the body of the semiconductor. 2. Never apply heat or molten solder to a lead or terminal for longer than 10 seconds or at a point closer than 1/16 of an inch to the body of the device. 3. Use a low voltage iron, 30 watts or less, specifically intended for use with transistors or miniature circuit components. 4. Keep the surfaces to be soldered clean and the tip of the soldering iron adequately tinned so that the connection can be made as quickly as possible. 5. Always use a heat sink on the lead when soldering. Gripping the lead or terminal with long nose pliers between the solder connection and the case or body allows the pliers to act as a heat sink, conducting heat away from the internal elements of the device. About case dimensions. In some instances, the case of an Archer semiconductor may be slightly taller or thicker than that of the original device or have a slightly different shape, particularly if the original device is a foreign type not made to USA, EIA and JEDEC standards. These mechanical differences should not affect the performance of the equipment in which the replacement is made and normally will not prevent or complicate the installation of the Archer replacement device. You should realize that cross-reference substitution listings are created based on electrical parameters, not necessarily on mechanical size or type. Thus, when you make substitutions based on our listings, check for physical-mechanical compatibility. If space is limited, it would be a good idea to check physical dimensions as well as electrical specs before making substitution. General precautions. Archer transistor and Archer semiconductors should not be inserted or withdrawn from circuits with the power on because transient currents may cause permanent damage to the device. In some cases, Archer semiconductors are in metal cans and thus could possibly become shock hazards if they are allowed to operate at a voltage appreciably above or below ground potential. For the most effective protection, a power transistor should be operated with an adequate heat sink and with the lowest value of resistance or impedance in the emitter to base circuit, consistent with driving signal considerations. The transistor, did I say transistor or transformer? For the most effective protection, a power transistor should be operated with an adequate heatsink and with the lowest value of resistance or impedance in the emitter to base circuit consistent with driving signal considerations. The transistor should be protected against extremely high collector voltage pulses which may be generated when the device is operated with inductive loads, particularly when current transients are present. When replacing a power transistor or rectifier which is attached to the equipment chassis or to a special heatsink, observe the following precautions. A. In the case of oxide-coated metal washers or wafers, which are frequently used as electrical insulators between the case of power transistors and the chassis or heatsink, it is important not to scratch, chip, or otherwise damage the oxide surface. B. When installing an Archer power transistor where a mica or oxide-coated metal washer was used to insulate the case of the original device electrically from the case, apply a thin coating of heat sink compound, Radio Shack number 2761372, between the washer and the chassis or heatsink. Testing a transistor. Before replacing a transistor, you want to be sure it needs to be replaced. Always check the entire circuitry to be sure the transistor requires replacement. The best method for checking transistors is to use a good transistor checker, dynamic in-circuit or out-of-circuit type. However, a sensitive VOM, which is a volt-ohm millimeter, which were popular back in the day, a sensitive VOM can give you a good indication of the quality of the device. Okay, and we're going to talk about in-circuit testing, and then we're going to out-of-circuit testing. So, in-circuit testing part A. First, check to see if the emitter-base junction is forward biased. An NPN transistor should show the base 0.2 to 0.65 volts positive with respect to the emitter, approximately 0.25 volts for germanium type, and 0.6 volts for silicon. A PNP transistor should show the same base, negative with respect to the emitter. So it's 0.25 volts for germanium and 0.6 volts for silicon. B. This is in-circuit testing part B. Check to see if the device is functioning as an amplifier. Short the emitter base junction to remove forward bias. Voltage at the collector lead should rise to approximately the potential of the collector supply bus line. Any difference is caused by ICES, which is the collector to base leakage current. The closer the collector voltage approaches the bus line, the lower ICES is, and the better the transistor. Part 2, out of circuit testing. Again, for the best indication of transistor quality, use a good transistor checker. However, an ohm meter can be used as described here. Before using the ohm meter or the ohmmeter, find out which polarity of the internal ohmmeter battery is connected to which test lead. Not all ohmmeters have the positive battery polarity connected to the red lead and the negative battery polarity connected to the black lead. To determine the polarity of the leads when using the ohmmeter function, use an external voltmeter or study the schematic of your VOM. Also, remember that in most transistor circuits, you are dealing with low voltages and currents, in some cases very low. Therefore, never use the RX1 scale. Extensive currents can flow through a junction, permanently damaging the transistor. It is best to determine the maximum amount of current available in each resistance range before using an ohmmeter for testing semiconductor junctions. After you have evaluated your VOM for the above and are sure you will not damage a transistor with excessive current or voltage in any given ohmmeter range, proceed as follows. A. Small signal PNP germanium. That doesn't seem. Proceed as follows. As follows. 5. Okay. A. Small signal PNP germanium transistors. 1. Connect the positive lead of your ohmmeter to the emitter. Connect the negative lead to the base. You should read 200 to 500 ohms. Connect the negative lead to the collector. You should read 10K to 100K. Shorting collector base. The resistance should decrease. B. Small signal NPN germanium transistors. Reverse the polarity of the leads. The reading should be approximately the same. C. Power PNP germanium transistors. Connect the positive lead to the emitter. Connect the negative lead to the base. The reading should be 35 to 50 ohms. 2. Connect the negative lead to the collector. The reading should be several hundred ohms. Shorting collector to base. The resistance should decrease. D. Power NPN germanium transistors. Reverse the polarity of the leads. The reading should be approximately the same. E. Small signal PNP silicon transistors. 1. Connect the positive lead to the emitter. Connect the negative lead to the base. The reading should be 1K to 3K. 2. Connect the negative lead to the collector. The reading should be very high. May show as open. F. Small signal NPN silicon transistors. Reverse the polarity of the leads. The reading should be approximately the same. G. Power PNP silicon transistors. Connect the positive lead to the emitter. Connect the negative lead to the base. The reading should be 200 to 1K ohms. 2. Connect the negative lead to the collector. The reading should be about 1 mega ohm or more. H. power NPN silicon transistors. Reverse the polarity of the leads. The readings should be approximately the same. The resistance readings noted above can only be approximate as long as you obtain somewhat proportionate readings, emitter-based readings as compared to emitter-collector. You can safely assume the transistor is okay. Handling of integrated circuits. Because MOS devices have extremely high input resistance, they are susceptible to damage when exposed to static electrical charges. Even electrical charges that normally build up on the human body can cause damage. To avoid possible damage to the devices during handling, testing, or actual operation, the following procedures should be observed. Except when being tested or in actual operation, the leads of devices should be in contact with the conductive material to avoid buildup of static charge. 2. Soldering iron tips. Tools, metal parts of fixtures and handling facilities should be grounded. 3. Transient voltages may cause permanent damage to the device if it is removed or inserted with the power on. 4. Do not apply signals to the inputs with the power supply off. 5. All unused input leads must be connected to either VSS or VDD, whichever is appropriate for the logic circuit involved. Diodes and rectifiers. General purpose diode ratings at 25 degrees Celsius. All right, so now what we're looking at is diodes and rectifiers, general purpose diodes, Zener diodes, bridge rectifiers, bipolar transistors, field effect transistors, and unijunction transistors. All right. So we're not going to go into great detail, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 different types of general purpose diodes. They've got 4 different types of Zener diodes. 6.2 volts, 9.1 volts, 12 volts, and 15 volts. We've got some bridge rectifiers. 1, 2, 3, 4, 5, 6, 7 of them. Cool. We've got transistors, a whole heap of bipolar transistors. And there's NPNs and PNPs and NPNs and PNPs. So there's all sorts of things. Material, germanium and silicon, direct commercial equivalent. Yeah, right. And voltage ratings, maximum current ratings. HFE is the beta value, which is the gain. Great. Look at this one, 20,000 gain. That's a monster. All right, note, all ratings given are for 25 degrees Celsius, except where otherwise noted. Material S for silicon, G for germanium. Application S for switch, LL for low level, RF for RF power, GP for general purpose, P for power amplification and switching, and HV for high voltage. And then we've got our field effect transistors. Are they MOSFETs? I assume they are. Maybe they're JFETs, I don't know. And unijunction, there's one device listed. And then we're up to display and optoelectronic devices. And we've got a thing here called the selenium solar cell. Selenium solar cell. Oh, that's down here, I see. So 0.6 inch, 7 segment numeric display. And it comes with the dot, so it's got 8 LEDs including the dot. General description. These devices are single-digit numeric displays. They're compatible with bipolar and MOS ICs. They provide fast switching, excellent for multi-point multiplexing. Excellent for multiplexing. Okay. And the 0.6 inch character height provides a viewing distance up to 25 feet. The 276056 is common anode. The 276066 is common cathode. Applications: digital clocks, elevator floor indicators, panel meters, calculators, and TV channel indicators. Absolute maximum ratings. Power dissipation at 960 milliwatts. Okay. Power D-rate factor, storage and operating temperature up to 85 degrees. DC current / segment or DP at 25 degrees, 30 milliamps. Average current segment or DP, 25 milliamps. Peak current, 250 milliamps. Reverse voltage, 6 volts. And solder temperature, 240 degrees Celsius. Typical characteristics: light intensity versus ambient temperature. Oh, there you go. So the temperature goes up and the intensity goes down. Forward current versus forward voltage. Okay, I see. Cool. Okay, and then they've got 18 pin common redundant anodes. Yeah, right. So we've got 18 pins. Yeah, okay. So it's a 9 and 9, which is 18 pins on these guys. Some of them aren't connected. Cathode, anode, cathode, anode. Yeah, right. So some of them have common anodes and some of them has common cathodes. And then we've got our selenium solar cell. General description: the selenium solar cell is a device that can change the energy of the sun into electrical energy for use in your electronic projects. It can be used in place of the battery, or it can be used as a lightweight sensor, or as a light sensor. It produces a 0.5 volt at 0.6 milliamps in strong sunlight, which is enough to power small radios and oscillator circuits. The unit is sensitive to the same range of light as the human eye. Okay. Features: dimensions 1.5 inch by 1 1/8 of an inch. That's pretty small. Sensitive area, lead type, weight, photoelectric characteristics, max voltage output 0.5 volts, max current output 0.6 milliamps, output at 100 lux, 50 microamps, output at 500 lux, 90 microamps. Peak spectral response, 5,500 angstroms. All right, now we've got cadmium sulfide photocell, silicon solar cell phototransistor, display and optoelectronic devices. That must be on the next page. Yeah, okay. So, cadmium sulfide photocell. A cadmium sulfide photocell is a light variable resistor which is most sensitive in the green to yellow portion of the light spectrum. With it, you can use light to control many electronic devices. Maximum resistance is 0.5 mega ohms, minimum resistance is 100 ohms, maximum voltage is 170 volts, max wattage 0.2 watts. Rugged epoxy case. Applications: night light, light control, burglar alarm, relay. Okay, features: shape is round, sensitive area is pretty small, weight is pretty low, resistance at 1 FTC. 1.7 kilo ohms. Typical resistance, 100 ohms. Resistance, dark, minimum, 0.5 mega ohms. Absolute maximum ratings. Okay, so max voltage 170 volts, max power 2 watts. Power D rating. Actually, they say here that it's 0.2 watts, and they say here that it's 2 watts, so something got lost there. Power D rating, linearly 0 to 75 degrees Celsius, operating range up to 75 degrees Celsius. Silicon solar cell. The silicon solar cell is a device that can change the energy of the sun into electrical energy for use in your electronic project. It can be used in place of a battery, or it can be used as a light sensor. Okay, so we've had a selenium solar cell, and now we're doing a silicon solar cell. Application: solar powered battery charger. Use several in series or parallel for added power. Power radio circuits. So the dimensions here, they've gone into metric all of a sudden. 2x4 and 2x2 options. And the maximum output voltage is 0.5 volt. That was the same as the selenium, but it can provide more current, up to 100 milliamps. There you go. And for the other model, it's 60 milliamps. Silicon phototransistor. The 3-terminal phototransistor has exceptionally stable characteristics and high illumination sensitivity. The electrically connected base lead increases its applicability to various circuit designs. It features low leakage, low power requirements, TTL/DTL compatibility. By the way, that's transistor logic and diode transistor logic. It was a family of logic specifications for voltage levels and such. A large range of sensitivities and minimal response time. Okay. You'd still probably get a silicon phototransistor today. We won't go through its maximum specs. So this is display and optoelectronic devices. We've got the 1.6 amp light activated silicon controlled rectifier. Oh, there we go. That's what the LA is for light activated. The light activated silicon rectifier is sensitive to both visible and invisible light. Light sensitivity up to 200 FT candles. I don't really know what that means. I'm not a lighting guy. Applications: on-time switch, optical switch, counting circuits, delay circuits, phase control. Clock display board, 4 to 0.5 digits with colon. Okay. Yeah, so you can put a clock on this. It's got the colon. So I don't know what the 4-0.5. Is there a 0.5 here somewhere? I don't know. General description. These devices are a 24-hour clock display with colon located between digits 2 and 3. This is a direct drive display consisting of 4 digits, 4 for hours and minutes, separated by a colon. It also has AM/PM indicator in the upper left-hand corner. Absolute maximum ratings. Okay, so there's a bunch of ratings there, and then it'll give you the pinout. Very good. And we've got LED display. Oh yeah, LED display, digital electronic clock module. Oh, I see. So was this one LED? I'm not sure. Clock display board. Doesn't say if it's LED or not. Presumably it's an LED, but over here they're saying it's liquid crystal. Did I see? No, LED display here. LED display. So colon direct drive display, 4 digits. I'm not sure if we're dealing with the LEDs or LCDs. I'm not sure. But here this is supposed to be LED. Electronic clock module combines a monolithic MOS LSI, LSI is for large scale integration, MOS LSI integrated clock circuit, four digit 0.5 inch. Oh, I see. 4 digit 0.5 inch LED display. So that's what this means. 4 0.5 inch digits. Oh, I see. Now I understand. Power supply and other associated discrete components on a single printed circuit board to form a complete electronic clock movement. The user need add only a transformer and switches to construct a pre-tested digital clock for application in clock radios, alarm or instrument panel clocks. Timekeeping may be from 50 or 60 hertz inputs. Direct non-multiplexed LED drive eliminates RF interference. Time setting is made easy through use of fast and slow scanning controls. Features: bright 4 digit 0.5 inch LED display, complete add-only transformer and switches. Alarm clock and clock radio versions, 12-hour display format, 50 or 60 hertz operation, power failure indication, brightness control compatibility, sleep and snooze timers, alarm on and PM indicators, direct drive, no RFI, fast and slow set controls, low cost compact design. So with that direct drive, no RFI, I think that means you don't have to multiplex each digit, which I assume that's what that's talking about. They did mention about it multiplex support earlier in the other one. Fast and slow set controls, low cost compact design. Applications: clock radio timers, instrument panel clocks, alarm clocks, desk clocks, TV stereo timers. And here's a schematic diagram. Very good. All right, 12 volt automotive instrument clock module. The MA1003 12 volt DC automotive instrument clock module combines the MM5377 monolithic MOS/LSI clock circuit, a 4-digit 0.3 inch green vacuum fluorescent display, a 2.097 megahertz crystal and supporting components to form a complete digital clock for 12 volt DC applications. The module is fully protected against automotive transients and battery reversal conditions, with timekeeping maintained down to 9 volt DC. Automatic display brightness. Control logic blanks the display with ignition off, reduces brightness to 33% with park or headlamps on, and follows the dash lamp dimming control setting. The display features leading zero blanking and has a blinking colon activity indicator. The bright green display color is filterable to various shades in the green, blue, and yellow color range. Time setting is accomplished by choosing hours advance and minutes advance switches. These switches are disabled when the display is blanked to prevent tampering. Interconnections are simplified through use of 6-pin edge connector. Display may be activated with ignition off or park headlights off by closing display switch, allowing minimum power consumption in portable applications. Features: ideal for automotive applications. Operates from 12 volt DC supply. Bright 0.3 inch green display. Internal crystal time base. Plus or minus 0.5 second per day accuracy. Protect against automotive voltage transients and reversals. Timekeeping maintained to 9 volt DC. Memory to 6 volt DC. Automatic display brightness control logic. Display color filterable to blue, green, and yellow. Complete, just add switches and lens. Convenient time setting controls at a 1 Hz rate with no rollover. Compact size, built-in connector, optional. Low standby power consumption. Lockout of time setting when display is off. Applications: in-dash auto clocks, aftermarket auto recreational vehicle clocks, aircraft marine clocks, 12-volt DC operated instruments, portable and battery powered instruments. There we go. Functional description: display brightness, brightness control, zero blinking, and on we go. Oh, they're going to keep going over here as well. So they're going to keep going through the functional description, talk about the ignition input, park lights input. There's a schematic diagram. Cool. Are we still going? I think we are. Yeah, schematic diagram, dash lamps, hours and minutes, display on. Typical applications. Okay, so it's showing you how to connect the clock and add in some switches for display brightness, parking lights. You can adjust the light level based on whether your parking lights are on or not. Electrical characteristics as a whole thing. Absolute maximum ratings. Table 1, display brightness. So this is basically just a 24-hour clock. Fair enough. All right. Up next, we've got a CPU. Wow. This is an 8080. It's a precursor to the 8086, I think. I don't know. I forget. I should know. This is an 8-bit N-channel microprocessor. The INS 8080A is an 8-bit microprocessor housed in a standard 40-pin dual inline package. The chip, which is fabricated using N-channel silicon gate MOS technology, functions as the central processing unit in National Semiconductor's N8080 microcomputer family. The INS 8080A has a 16-bit address bus that is capable of addressing up to 65K bytes of memory and up to 256 input and 256 output devices. Data is routed to and from the INS 8080A on a separate bidirectional 8-bit bus. This data bus is also tri-state, making direct memory addressing, DMA, and multiprocessing applications possible. The INS 8080A directly provides signals to control the interface to memory and I/O ports. All buses, including control, are TTL compatible. An asynchronous interrupt capability is included in the INS 8080A to allow external signals to change the instruction sequence. The interrupting device may vector the program to a particular service routine location or some other direct function by specifying an interrupt instruction to be executed. Features: 2 microsecond instruction cycle, variable length instructions, general purpose registers 6 plus an accumulator, direct addressing up to 665 kilobytes, variable length stack accessed by a 16-bit stack pointer, addresses 256 input and 256 output ports, provision for vectored interrupts, tri-state bus for DMA and multiprocessing capability, tri-state TTL drive compatibilities for address and data buses, decimal arithmetic compatibility, multiple addressing modes: direct, register, register indirect, immediate, direct plug-in replacement for Intel 8080A. There we go. So it was the Intel 8080, and it looks like National Semiconductors made a knockoff. Functional pin definition. The following describes the function of all of the INS 8080A input-output pins. Some of these descriptions reference internal timing periods. Input signals: ready, hold, interrupt request, reset. Is that theta or 01 and 02 clocks? 12 volts ground, plus 5 volts ground, minus 5 volts. Output signals, sync, address, okay, the address bus, 16 bits, wait, write, hold, acknowledge, interrupt, enable, data bus in, input output signals, 8-bit bus for input and output, okay, and 8080A status. Instructions for the 8080A require from 1 to 5 machine cycles for complete execution. The 8080 sends out 8 bits of status information on the data bus at the beginning of each machine cycle during sync time. The following table defines the status information. So the status information, it's got 1, 2, 3, 4, 5, 6, 7, 8 bits. Okay. There's int A, WO, write out, stack. Okay, we've got int A, acknowledge signal for interrupt request. Signal should be used to gate a restart instruction onto the data bus when dbin is active. WO indicates that the operation in the current machine cycle will be a write memory or output function. WO equals 0. Otherwise, a read memory or output interruption will be executed. Okay, so it's active low. When it's 0, there's a write. Otherwise, it's 1 and it's a read. Stack indicates that the address bus holds the pushdown stack address from the stack pointer. HLTA, acknowledge signal for halt instruction. Okay. Out indicates that the address bus contains the address of an output device and the data bus will contain the output data when WR is active. Okay, I'm not sure what WR is anyway. M1 provides a signal to indicate that the CPU is on the fetch cycle for the first byte of an instruction. In P indicates that the address bus contains the address of an input device and the input data should be placed on the data bus when dbn is active. Okay, don't know where dbn is. Must have been this other stuff here. And there's one called MEMR. Designates that the data bus will be used for memory data read. All right. And then it's got various capacitance on some of the pins by the looks of it. Some electrical characteristics, a lot of voltages, few currents. Status word chart. It's pretty good that they can give you a whole CPU spec in a couple of pages. So get some absolute maximum ratings. We've got a block diagram. Fair enough. So I think, yeah, the box here is the INS 8080A, and you can connect it to ROMs, RAMs, parallel I/O interface, serial I/O interface, extended capability, optional buffers and decoders, system controller. Okay. What's over here? Clock generator. I see. Maybe that's what those Phi 1 and Phi 2 were, was clocks. CPU functional block diagram. Awesome. Timing waveforms. Wow. Look at that. Note 1. This timing diagram shows timing relationships only. It does not represent any specific machine cycle. Note 2. Data in must be stable for this period. Okay, so it's going to go through all the details of the timing. We're not going to look at that, but good to know that it's well specified. All right. Yes, now we're going to get into some logic stuff. Can you see that? So what have we got? Okay, I'm just going to take 2 seconds. I'll be back. All right, so I just went and checked, and I did know this somewhere in the back of my head. The 74 series integrated circuits were the original TTL circuits. But these days you don't see 74C, you see 74HC or 74LS. But I guess in the olden days they were C. And apart from that, the numbers are still the same. So you can still get these quad 2-input NAND gates, quad 2-input NOR gates, and the hex inverters. And they're logically the same, but the implementation varies. And I think a lot of the 7.4 series stuff, you can actually get it in CMOS implementations now. Oh, no, it says here that they're using MOS. Okay. But the TTL specifications, they must have internal interface for TTL compatibility, I guess. Anyway, let's just let's read what they have to say about the 74C00, 74C02, and 74C04. Looks like quad 2-input NAND gate, quad 2-input NOR gate, and a hex inverter. General description: these logic gates employ complementary CMOS, to achieve wide power supply operating range, low power consumption, high noise immunity, and symmetric controlled rise and fall times, with features such as the 74C logic. With features such as this, the 74C logic family is close to ideal for use in digital systems. Function and pin-out compatibility with Series 74 devices minimizes design time for those designers already familiar with the standard 7.4 logic family. Okay, so this is the 7.4C logic family, which I don't think you'll find really today. I don't know, maybe you can get it still, I don't know. All inputs are protected from damage due to static discharge by diode clamps to VCC and ground. Oh, that was a good idea. Features: wide supply voltage range, 3 volts to 15 volts, guaranteed noise margin, 1 volt, high noise immunity, 0.45 VCC typical, low power consumption, 10 nanowatts per package typical, low power TTL compatibility, fan out of 2 driving 74L. And then with some maximum ratings, and then we're on to the 74C08, which is the quad 2-input AND gate. Okay. General description: employing complementary MOS, CMOS transistors to achieve wide power supply operating range, power consumption, and high noise margin. These gates provide basic function used in the implementation of digital integrated circuit systems. The N and P channel enhancement mode transistors provide a symmetrical circuit with output swing essentially equal to the supply voltage. No DC power other than that caused by leakage current is consumed during static condition. All inputs are protected from damage due to static discharge by diode clamps to VCC and ground. Features are basically the same as the earlier ones. Wide supply voltage range, 3 volts to 15 volts. Guaranteed noise margin at 1 volt. High noise immunity at 0.5 volts. VCC typical. Low power TTL compatibility, fan out of 2 driving 74L. low power consumption, 10 nanowatts per package typical. All right, then we've got a dual D flip-flop as a logic diagram. General description. The 74C74 dual D flip-flop is a monolithic complementary CMOS integrated circuit constructed with N and P channel enhancement transistors. Each flip-flop has independent data, preset, clear, and clock inputs, and a Q and inverted Q outputs. The logic level present at the data input is transferred to the output during the positive going transition of the clock pulse. Preset or clear is independent of the clock and accomplished by a low level at the preset or clear input. Applications: automotive, data terminals, instrumentation, medical electronics, alarm system, industrial electronics, remote metering, computers. Features: supply voltage range 3 to 15 volts, 10th power TTL compatibility, 2 LPT 2L loads, high noise immunity, low power, medium speed operation at 10 megahertz with 10 volt supply. And there's some absolute maximum ratings. And we've got dual JK flip-flops with clear and preset. And we've got the pinout and the logic diagram. Again, very good. General description: these dual JK flip-flops are monolithic complementary CMOS integrated circuits constructed with N and P channel enhancement transistors. Each flip-flop has independent JK clock and clear inputs and Q invert outputs. The 74C76 flip-flops also include preset inputs and are supplied in 16-pin packages. These flip-flops are edge sensitive to a clock input and change state on the negative going transition of the clock pulses. Clear or preset is independent of the clock and is accomplished by a low level on the respective input. Applications: automotive, data terminals, instrumentation, medical electronics, alarm systems, industrial electronics, remote metering, and computers. Okay, 4-bit decade counter. The 74C90 general description. The 74C90 decade counter is constructed with N and P channel enhancement mode transistors. The 4-bit decade counter can be reset to 0 or preset to 9 by applying appropriate logic level on the R01, R02, R91, and R92 inputs. Also, a separate flip-flop on the A bit enables the user to operate it as a divide by 2, 5, or 10 frequency counter. All inputs are protected against static discharge damage. And they've given us the pin diagram and a logic diagram. Cool. Now we're up to synchronous 4-bit up-down decade and synchronous 4-bit up-down binary. So it sounds like you can put, oh no, one's a decade counter and one's a binary counter. So, okay, you're going to have to decide. And for the decade, does it use BCD? It does. I'll just read this. General description. These up-down counters are monolithic complementary CMOS integrated circuits. The 74C192 is a BCD counter. That's binary coded decimal. While the 74C193 is a binary counter. Counting up and counting down is performed by 2 count inputs, one being held high while the other is clocked. The output change on the positive going transition of this clock. These counters feature preset inputs that are set when the load is a logical 0 and a clear, which forces all outputs to 0 when it is at logical 1. The counters also have carry and borrow outputs so that they can be cascaded using no external circuitry. Very good. Features: high noise margin, 1 volt guaranteed, 10th power TTL compatible drive to LP TTL loads. Okay, wide supply range 3 volt to 15 volt, carry and borrow outputs for n bit cascading, asynchronous clear, high noise immunity, 0.5 VCC typical. There's some absolute maximum ratings. And then we're on to the, now we're on to the 4000 series logic, which is also CMOS logic. Quad 2 input NOR gate. So, the 4001 quad 2 input NOR gate is constructed with MOS P-channel and N-channel enhancement mode devices in a single monolithic structure. These complementary MOS gate logic gates find primary use where low power dissipation and or high noise immunity is desired. This device contains circuitry to protect the inputs against damage due to high static voltages or electric fields. However, it is advised that normal precautions be taken to avoid application of any voltage higher than maximum rated voltages to this high impedance circuit. For a proper operation, it is recommended that V-in and V-out be constrained to the range VSS is less than V-in or V-out is less than, I'm not quite sure about that. Okay, okay. So VSS should be low and VDD should be high and everything in and out should be in between. Unused inputs must always be tied to an appropriate logic level, either VSS or VDD. Features: quiescent current, 0.5 nanoamps, not very much. Noise immunity, 45% of VDD typical. Diode protection on all inputs. Supply voltage range, 3 to 16 volts. Single supply operation, positive or negative. High fan out, greater than 50. High impedance, 10 to the 12 ohms typical. That's pretty big. Logic swing independent of fan out. Okay. And then we're up to the quad 2 input NAND gate, the 4011. The 4011 is constructed with P and N channel enhancement mode devices in a single monolithic structure, CMOS. Their primary use is where low power dissipation and or high noise immunity is desired. This device contains circuitry to protect and blah blah blah. So on we go. It's the same as it was for the NOR gates. This is the AND gates. It's given us the pin connections and the circuit schematic. Cool. Made with a couple of FETs. Easy peasy. Alright, now we're on to the 4000 series dual type D flip-flop. So the 4013 dual type D flip-flop is constructed with MOS, P-channel and N-channel enhancement mode drivers in a single monolithic structure. Each flip-flop has independent data, direct set, direct reset and clock inputs, and complementary outputs for Q and Q invert. These devices may be used as shift register elements or as type T flip-flops for counter and toggle applications. There you go. Features: static operation, quiescent current, noise immunity, diode protection on all inputs, supply voltage range 3 to 16 volts, single supply operation, toggle rate 4 megahertz, typical at 5 volts. Logic edge clock flip-flop design. Logic state is retained indefinitely with clock level either high or low. Information is transferred to the output only on the positive going edge of the clock pulse. Capable of driving 2 low power TTL loads, 1 low power Schottky TTL load or 2 HTL loads over the rated temperature range. There you go. We got a truth table there for the flip-flop. Very good. All right, then we've got the 4017. This is a decade counter. So we saw a decade counter earlier. Is it going to say BCD? It probably is. Doesn't seem to be jumping out at me. The 4017 is a 5-stage Johnson decade counter with built-in code converter. High-speed operation and spike-free outputs are obtained by use of a Johnson decade counter design. The 10 decoded outputs are normally low. I'll just be back in a sec. All right, so this decade counter, it just outputs the current count on logic pins. So it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different pins to indicate the current count. It can count from 1 to 10. All right, so okay, we've got a 14-bit binary counter. Wow. The 4020 14-stage binary counter is constructed with MOS P-channel and N-channel enhancement mode devices in a single monolithic structure. This part is designed with an input wave shaping circuit and 14 stages of ripple carry binary counter. The device advances the count on the negative going edge of the clock pulse. Applications include time delay circuits, counter controls, and frequency dividing circuits. This device contains circuitry to protect the inputs against damage due to high static voltages or electric fields. However, it is advised that normal precautions be taken to avoid application of any voltage higher than maximum rated voltages to this high impedance circuit. For proper operation, it is recommended that V in and V out be constrained to the range VSS through VDD. Unused inputs must be tied to ground or tied to VSS or VDD. Okay, so features: fully static operation. The alternative is dynamic, right? With where they use a capacitor and they have to rewrite the thing. So it yeah, okay. As a general rule, static is more reliable and it's but it's more expensive. Here's our cascaded adders in the logic diagram. Very good. Okay, now we're up to the dual JK flip-flop, the 4027. General description: the 4027 dual JK flip-flop has independent JK clock set and reset inputs for each flip-flop. And how many? There is 2 flip-flops. It's a dual package. These devices may be used in control, register, or toggle functions. This device contains circuitry to protect the inputs against damage, blah, 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 blah. It's all the standard CMOS disclaimers. Features: quotient current 2 nanoamps, noise immunity 45% of VDD typical, diode protection on all inputs, supply voltage range 3 to 16 volts, and on we go. All right, we've got 6 buffers. We've got inverting and non-inverting buffers. So the inverting buffer is first. The 4049 hex inverter / buffer and the 4050 non-inverting hex buffer are constructed with MOS P-channel and N-channel enhancement mode devices in a single monolithic structure. These complementary MOS devices find primary use where low power dissipation and or high noise immunity is desired. These devices provide logic level conversion using only one supply voltage VCC. The input signal high level VIH can exceed the VCC supply voltage for logic level conversions. 2 TTL/DTL loads can be driven when the devices are used as CMOS to TTL/DTL converters. Okay, you can actually use this to do the level conversions. There you go. Note that pin 16 is not connected internally on these devices. Consequently, connections to this terminal will not affect circuit operation. There you go. Features: high source and sink currents, high to low level converter, quiescent current 2 nanoamps, supply voltage range 3 to 16 volts. And here's the this is just a single inverter. So the inverting buffer is easier to make than the non-inverting buffer. There you go. All right, now what have we got? 4511, the BCD to 7 segment latch decoder driver. The 4511 BCD to 7 segment latch decoder driver is constructed with complementary CMOS enhancement mode devices and NPN bipolar output drivers in a single monolithic structure. The circuit provides the functions of a 4-bit storage latch, an 8421 BCD to 7 segment decoder, and an output drive capability. Lamp test LT, blanking, and latch enable inputs are used to test the display and to store a BCD code, respectively. It can be used with 7-segment light emitting diodes, LED, incandescent, fluorescent, gas discharge, or liquid crystal readouts either directly or indirectly. Applications include instrument, for example, counter, DVM, etc., display driver, computer/calculator display driver, cockpit display driver, and various clock, watch, and timer uses. This device contains circuitry to protect the inputs. Due to the sourcing capability of this circuit, damage can occur to the device if VDD is applied and the outputs are shorted to VSS and are at a logical 1. See maximum ratings. Unused inputs must be tied to an appropriate logic level, either VSS or VDD. Features: quiescent current 5 nanoamps, low logic circuit power dissipation, high current sourcing outputs up to 25 milliamps, large latch storage of code, blanking input, lamp test provision, readout blanking on all illegal input combinations. Oh, that's interesting. Lamp intensity modulation capability, timeshare multiplexing facility, supply voltage range, capable of driving 2 low power TTL loads. So what it's talking about there, I think, when they talk about timeshare multiplexing, what you can do is you can just put one digit on and just sort of flash it, and then flash it off and flash on the next one and turn it on, and they all flash because they flash so quickly. They seem to be constantly on, but that can have artifacts that you'll pick up with cameras and such like that. The flashing becomes visible on some recordings. Anyway, so this is the BCD to 7 segment display driver. Very good. We've got a dual BCD up counter. Okay. The 4518 dual BCD counter is constructed with MOS-P channel and N-channel enhancement mode devices in a single monolithic structure. It consists of 2 identical, independent, internally synchronous 4-stage counters. The counter stages are Type D flip-flops with interchangeable clock and enable lines for incrementing on either the positive going or negative going transition as required when cascading multiple stages. Each counter can be cleared by applying a high level on the reset line. In addition, the 4518 will count out of all undefined states within 2 clock periods. These complementary MOS up counters find primary use in multi-stage synchronous or ripple counting applications requiring low power dissipation and or high noise immunity. And then they've got the standard CMOS blurb and talking about tying unused inputs to a logic level. So there's the pinout. Got two of these BCD counters, and they've given the truth table here. Very good. Okay, now we've got a 301, the operational amplifier. Okay. The 301 is a monolithic operational amplifier intended for general purpose applications. Operation is completely specified over the range of voltages commonly used for these devices. The design, in addition to providing high gain, minimizes both offset voltage and bias currents. Further, the Class B output stage gives a large output capability with minimum power drain. External components are used to frequency compensate the amplifier. Although the unity gain compensation network specified will make the amplifier unconditionally stable in all feedback configurations, compensation can be tailored to optimize high frequency performance for any gain setting. The fact that the amplifier is built on a single silicon chip provides low offset and temperature drift at minimum cost. It also ensures negligible drift due to temperature gradients in the vicinity of the amplifier. There you go. So we've got some typical applications here. We've got a variable capacitance multiplier, simulated inductor, fast inverting amplifier with high input impedance, inverting amplifier with balancing circuit, sine wave oscillator. Oh, that's interesting. And an integrator with bias compensation. There you go. So that's the LM3301. And now we've got the LM 324. The 324 series consists of 4 independent high-gain, internally frequency compensated operational amplifiers, which were designed specifically to operate from a single power supply over a wide range of voltages. Operation from split power supplies is also possible, and the low power supply current drain is independent of the magnitude of the power supply voltage. Application areas include transistor amplifiers, DC gain blocks, and all the conventional op-amp circuits, which now can be more easily implemented in single power supply systems. For example, the 324 series can be directly operated off the standard 5-volt DC power supply voltage, which is used in digital systems, and will easily provide the required interface electronics without requiring the additional plus or minus 15-volt DC power supplies. Cool. Features: internally frequency compensated for unity gain, large DC voltage gain 100 decibels, wide bandwidth unity gain 1 megahertz, temperature compensated, wide power supply range from single supply to 30 volts, 3 to 30 volts, or dual supplies. Okay, very low supply current drain, low input biasing against 45 nanoamps DC, temperature compensated, low input offset voltage 2 millivolts DC, and offset current 5 nanoamps DC. Input common mode voltage range includes ground, differential input voltage range equal to the power supply voltage, large output voltage swings from 0 volts to V plus minus 1.5. I think that's trying to say. All right, so here's some. Oh, that's cool. They gave the schematic. Did they give the schematic for the LM301? Pin connection. No, they didn't give the schematic. They gave the pin connection. Okay, but here they actually gave the schematic, but just for one of them, one of the modules. Cool. And they're mostly bipolar. They're not FETs. So the amplifier is using BJTs. It's very good. So typical applications: driving TTL, voltage follower, pulse generator, square wave oscillator, pulse generator as another pulse generator, high compliance current sink. Yeah, right. And then we've got the LM339, which is the quad comparator. So, general description. The 339 series consists of 4 independent voltage comparators, which were designed specifically to operate from a single power supply over a wide range of voltages. Operation from split power supplies is also possible, and the low power supply current drain is independent of the magnitude of the power supply voltage. These comparators also have a unique characteristic in that the input common mode voltage range includes ground, even though operated from a single power supply voltage. Okay. Features: wide single supply, voltage range 2 volts to 32 volts, or dual supplies, plus or minus 1 volt to plus or minus 16 volt. Very low supply current drain. Input common mode voltage range includes ground. Differential input voltage range equal to the power supply voltage. Low output 1 millivolt at 5 microamp. Saturation voltage 70 millivolts at 1 milliamp. Output voltage compatible with TTL, fan out of 2, DTL, ECL MOS, and CMOS logic systems. Alright, and they've got the diagram there as well. And they are bipolar junction transistors again. Very good. Typical applications, 5 volt group, okay, the 5 volt group is a basic comparator, driving CMOS, driving TTL, and then the 15 volt group, an AND gate, an OR gate, a one-shot multivibrator, and a bistable multivibrator. Cool. Dual 2 watt audio amplifier. Dual 2 watt audio amplifier. This is the LM377. General description: the 377 is a monolithic dual power amplifier which offers high quality performance for stereo phonographs, tape players, recorders, and AM/FM stereo receivers, etc. The 377 will deliver 2 watts per channel into 8 or 16 ohm loads. The amplifier is designed to operate with a minimum of external components and contains an internal bias regulator to bias each amplifier. Each device overload protection consists of both internal current limit and thermal shutdown. Okay, so this is a dual 2 watt audio amp. There you go. They didn't give us the schematic, they gave us the pinout and some typical applications. Might as well read the features and the application. So AVO typical 9 dB, 9 decibels, 2 watts per channel, 70 decibel ripple rejection, 75 decibel channel separation, internal stabilization, self-centered biasing, 3 mega ohm input impedance, 10 to 26 volt operation, internal current limiting, internal thermal protection. Applications: multi-channel audio systems, tape recorders and players, movie projectors, automotive systems, stereo phonographs, bridge output stages, AM/FM radio receivers, intercoms, servo amplifiers, instrument systems. Then we've got some max ratings. Typical application: simple stereo amplifier, 10 watt per channel audio amplifier, simple stereo amplifier with bass boost, and 4 watt bridge amplifier. And we've got low voltage audio power amplifier, the LM386. General description: the 386 is a power amplifier designed for use in low voltage consumer application. The gain is internally set to 20 to keep external part count low, but the addition of an external resistor and capacitor between pins 1 and 8 will increase the gain to any value up to 200. The inputs are ground reference, while the output is automatically biased to 1/2 the supply voltage. The quiescent current drain is only 18 milliwatts when operating from a 6 volt supply, making the 386 ideal for battery operation. Features: Battery operation, minimum external parts, wide supply voltage range 4 to 12 volts, low quotient current drain of 3 milliamps, voltage gains from 2 to 200, ground reference input, self-centering output quotient voltage, low distortion, 8-pin dual inline package. And they've given the schematic diagram as well. And it's all built out of resistors and bipolar junction transistors. Typical characteristics. Okay, so we've got distortion versus frequency. Okay, distortion versus output power. Device dissipation versus output power, 4 ohm load. Device, and then we've got same again, 8 ohm load, and same again, 16 ohm load. Okay. This is a log scale here on the output power. Typical applications. Amplifier with gain equals 20, minimum parts. Amplifier with gain 200. We're going to add in the capacitor here. There's a capacitor here as well. Okay. And then amplifier with gain 50. That's got a resistor and a capacitor. I see. Cool. Voltage regulator. LM723. Interesting. The 723 is a voltage regulator designed primarily for series regulator applications. By itself, it will supply output currents up to 150 milliamps, but external transistors can be added to provide any desired load current. The circuit features extremely low standby current drain, and provision is made for either linear or foldback current limiting. Features 150 milliamp output current without external pass transistor. Output currents in excess of 10 amps possible by adding external transistors. Input voltage 40 volt max. Output voltage adjustable from 2 volts to 37 volts. Can be used as either a linear or a switching regulator. The 723 is also useful in a wide range of other applications such as a shunt regulator, a current regulator, or temperature controller. And we've got the pin connections and a typical application. Great. And we've got the 741 operational amplifier. The 741 series are general purpose operational amplifiers which feature improved performance over industry standards. The amplifiers offer many features which make their application nearly foolproof: overload protection on the input and output, no latch up when the common mode range is exceeded, as well as freedom from oscillations. So maximum ratings, we've got the pin connection. It's one of those circular jobbies again. And there's a dual inline package as well. Cool. Non-inverting amplifier is a typical application. Cool. I'll take a break. Up next, a dual operational amplifier. So there's 2 amplifiers in the package here. General description: the 1458 is a general purpose dual op amp. The 2 amplifiers share a common bias network and power supply leads. Otherwise, their operation is completely independent. Features include no frequency compensation required, short circuit protection, wide common mode and differential voltage ranges, low power consumption, no latch up when input common mode range is exceeded. Then we've got the quad operational Norton amplifier, the 3900. General description: the 3900 series consists of 4 independent dual input internally compensated amplifiers which were designed specifically to operate off of a single power supply voltage and to provide a large output voltage swing. These amplifiers make use of a current mirror to achieve the non-inverting input function. Application areas include AC amplifiers, RC active filters, low-frequency triangle, square wave, and pulse waveform generation circuits, tachometers, and low-speed, high-voltage digital logic gates. Oh, that's interesting. Features: wide supply voltage, 4 volt to 36 volt, or dual supplies, plus or minus 2 volts to plus or minus 18 volts. Supply current drain independent of supply voltage. Low input biasing current at 30 nanoamps. High open loop gain, 70 decibels. Wide bandwidth, 2.5 megahertz at unity gain. Large output voltage swing, V plus minus 1 VP to P. Internally frequency compensated for unity gain. Output short circuit protection. There's typical applications are a basic instrumentation amplifier. Okay. All right, now we're up to a temperature controller. The 3911 is a highly accurate temperature measurement and or control system for use over negative 25 degrees Celsius to positive 85 degrees Celsius temperature range. Fabricated on a single monolithic chip, it includes a temperature sensor, a stable voltage reference, and an operational amplifier. The output voltage of the 3911 is directly proportional to temperature in degrees Kelvin at 10 millivolts per degrees Kelvin. Using the internal op-amp with external resistors, any temperature scale factor is easily obtained. By connecting the op-amp as a comparator, the output will switch as the temperature traverses the set point, making the device useful as an on-off temperature controller. An active shunt regulator is connected across the power leads of the 3911 to provide a stable 6.8 volt reference for the sensing system. This allows the use of any power supply voltage with suitable external resistors. Features: uncalibrated accuracy, plus or minus 10 degrees Celsius. Okay, that's pretty terrible. But presumably you can calibrate it. Internal op-amp with frequency compensation. Linear output of 10 millivolts per degree Kelvin, which is 10 millivolts per degree Celsius. Oh yeah, okay, they're the same. Can be calibrated on degrees Kelvin, Celsius, or Fahrenheit. Output can drive loads up to 35 volts. And we get some maximum ratings and a bunch of typical applications. So we've got a ground referred centigrade thermometer, basic temperature controller, basic thermometer for negative supply, basic thermometer for positive supply, and proportioning temperature controller, and an increased gain and output drive. Okay. And we've got a MOS LSI digital clock / calendar radio timer. Okay. So, MOS is metal oxide semiconductor, and LSI is large scale integration, which in 1978 was probably state of the art. Of course, then we got VLSI, and now we don't. We talk about process size and such, and it's all changed. But LSI, large scale integration. So it's a fairly sophisticated chip is LSI. It's not super high sophisticated, but it was at the time, I think. All right, general description. The 7001 is an alternating time, 8-second display, and calendar, 2-second display chip. Okay. To construct this clock / calendar circuit, you need only a single power supply, displays, and standard interface components. Power supply, displays, and standard interface components. It is compatible with 4 or 6-digit 7-segment common cathode multiplex displays. Okay, it does multiplex them. It means it flashes them on and off. Features: 28, 30, 31-day calendar, 24/12 hour clock, and 24-hour alarm with 10-minute snooze control. 50-60 hertz operation, 9-hour 59-minute timer, on-chip 60 hertz backup, 1 hertz output, and an inhibit input to wire OR. I'm not sure what that means. The digit and segment outputs to other chips. The setting of any one counter, time, alarm, calendar, timer does not affect the contents of any other counter. Okay, and there's a bunch of maximum specs. And we've got chemical. It must be on the next page. Gee, that's quite a bill of materials they've got there. Wow. Okay. So I've got a little bit of a bent page here. You can see that the integrated circuit's the heart of this thing. Oh no, it's over. Is it over here? I'm not sure. Let's have a look. Oh, okay. So this is the integrated circuit in the middle here, and we've got some buffers, inverting buffers. All right, cool. So this is how to make your own clock radio using their integrated circuit. And there's a bunch of capacitors. So those other things are segment drivers, and there's a hex driver, clock, calendar, radio, timer, integrated circuit 1756. Oh, I see. Yeah, fair enough. Then on to voltage regulators. Very good. So what have we got? The LM. Oh no, it's not the LM. It's the MU A78XX. There we go. 7805, 7812, and 7815. There we go. And the XX indicates the voltage. Great. This series of three terminal regulators is available with several fixed output voltages, making them useful in a wide range of applications. One of these is local on-card regulation, eliminating the distribution problems associated with single-point regulation. The voltages available allow these regulators to be used in logic systems, instrumentation, hi-fi, and other solid-state electronic equipment. Although designed primarily as fixed voltage regulators, these devices can be used with external components to obtain adjustable voltages and currents. This series will allow 1.5 amp load currents if adequate heat sinking is provided. Current limiting is included to limit the peak output current to a safe value. Safe area protection for the output transistor is provided to limit internal power dissipation. If internal power dissipation becomes too high for the heat sinking provided, the thermal shutdown circuit takes over, preventing the IC from overheating. Oh, that's good. Features: internal thermal overload protection, no external components required, output transistor safe area protection, internal short circuit current limit. Voltage range 5, 12, and 15 volts, absolute maximum ratings. And then we've got typical applications include plus or minus tracking voltage regulator, switching regulator, current regulator, high output current short circuit protected, positive and negative regulator. All right. How does that work? Use 2 of them. Oh, I see. Yeah. So they're tied to the AC with the transformer and 2 separate secondaries. Yeah, and it goes positive and it goes negative. Fascinating. All right, I'm going to take a quick break. All right, well, I just went and got myself a fresh coffee. So, very important. Looks like up next is RAM, static RAM. That would have cost a pretty penny back in the day. So, let's make some room for my coffee here. This is 124-bit static random access memory. The 21L02 is a 124-bit random access memory fabricated with high density, high reliability, N-channel silicon gate technology. For ease of use, the device operates from a single power supply, is directly compatible with TTL and DTL, and requires no clocks or refreshing because of static operation. This device, I'm actually kind of pleased that they had all this figured out by 1978. It's 1978. It wasn't really completely the dark ages. You thought it might have been. 1978, it's a long time ago. But they already knew about DRAM and SRAM, and yeah, they already had CMOS technology. So they'd gone well past TTL and DTL only. So yeah, I'm impressed. That's before I was born. So yeah, that's good to know. This device contains circuitry to protect the inputs against damage due to high static voltage or electric fields. However, it is advised that normal precautions be taken and blah, blah, blah. Features 128, 1024 word by 1 bit organization. I'm not sure what that really means. Access time is it says access time as nanoamps. Why would it say nanoamps for time? Does it mean nanoseconds? Or is it some power thing? I don't know. If you know what the access time equals 450 nanoamps means, I'd be interested to know. Low power dissipation, 150 milliwatts, typical. Static operation, single plus 5 volt supply line. Direct TTL/DTL compatibility, 3-state output, chip enable for memory expansion, cost-effective data storage, recommended DC operating conditions, absolute maximum ratings, logic diagram. So the address. Okay, so I'm a bit confused. How many address pins does it have? Let's see. A0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's got 9 address. Okay, and then there's D out. Oh, I see. Okay. So hang on a sec. All right, well, I had to think carefully about that. So first of all, the address lines numbering start at 0 and they go through to 9, which means there's 10 bits. 10 bits for the address. So the memory only addresses 1 bit at a time. There you go. So there's yeah, a 10 bit address and a 1 bit random access memory. 1-bit output. Or input, depending on if you're reading or writing. All right, so next we've got quadruple 2-input NAND gate. Okay, so we're up to the 7.4. These are more 7.4 series. Oh, I see. So that the 7.4 series we saw earlier, those are 7.4C, which is probably C for CMOS. What do you reckon? Was it before or after this? I forget. I'm not sure. Anyway, we're doing some more 7000 series, and this was the original TTL logic. That's what we're looking at here. So we've got TTL 7400 series. So this is the original. This is the oldest type of digital logic. It uses TTL. There was stuff that came before TTL, but TTL came before CMOS, and a lot of the stuff we just saw is CMOS. This is not CMOS. I don't know if they're going to give us any internals. No, it's just it's all just logic gates that they're showing us. They're not showing us how it's actually made internally, which they did do earlier a couple of times. Anyway, we should be able to fly through this. Let's just say that we've got quad 2 input NAND gates. Okay, and then we've got quad 2 input NOR gates, and then we've got hex inverter, which means 6 inverters. The inverters seem to require fewer parts if they're inverters than just buffers. And I don't know what the difference between those is. We've got a hex inverter, and then we've got a hex inverter buffer / driver. It must be able to drive more current. It's output current 40 milliamps, and here 10 milliwatts. It didn't give it to us in amps, but it's less. So there you go. So the buffer can provide more power. Very good. Quad 2 input AND gate. Okay, so we've got an AND gate. Okay, then we've got the old 3 input NAND gate, and there's only 3 of them, so it's a 333 input. Very good. Okay, now we've got what's called a dual Schmidt trigger. The 7413 is a dual Schmidt trigger with input gating. It differs from a conventional dual 4-input gate in that instead of having a single threshold voltage, the 7413 has different thresholds for positive and negative going inputs. When the output is in the logical 0 state, an input must be lowered to the 0.9 volts typically before the output changes state. Conversely, in order to return to the logical 0 state, the output must rise to 1.7 typically. This hysteresis is extremely beneficial in application where slow rise and fall time signals are prevalent. Okay, cool. So, yeah, so that they call this hysteresis. And what it means is because what happens when you've got a signal that turns something off and on, if it's just hovering around the middle, it'll keep swapping in and out of the state, and it can just start oscillating and being silly. And when you're doing something like turning an air conditioner on or off, you don't want to constantly be turning it off and back on again because that really wears it out. So this has some hysteresis, and it'll wait until you exceed a maximum before it does the thing, and then it'll wait till you've exceeded a minimum before it does the thing. So it says here applications are pulse shaper and threshold detector. Fair enough. Now we've got dual 4-input NAND gate. Okay, so there's 2 of them and they're 4 inputs. And then we've got a triple 3-input NOR gate. Very good. And we've got quad 2-input OR gate. Okay. BCD to decimal decode driver. The 7441 is monolithic binary coded decimal to decimal decoder. The BCD number to be decoded is applied to the 4 input lines. The unique output corresponding to the decimal equivalent of the input number falls to a logical 0 level. Outputs are designed to drive gas-filled readout tubes, but are also able to operate with other low current amps and lamps and relays. An overrange feature provides that if binary numbers between 10 and 15 are applied to the input, the least significant bit of these numbers, 0 through 5, will be decoded on the output. There you go. And does it have... Right. Yep, there they are. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 0 to 9. So there's there's a pin for each level. Very good. All right, now we've got a BCD to 7 segment decoder / driver. Great. It's given the logic diagram here. Excellent. So this is just for interfacing a BCD, which is 4-bit number that represents the values 0 to 9, plus a few hexadecimal ones as well, actually. I don't know if the driver will support them. Let's see what it says. This versatile series of 7-segment display drivers fulfills a wide variety of requirements for most active high, common cathode, and active low, common anode, light-emitting diodes or lamp displays. Each device fully decodes a 4-bit BCD input into a number from 0 through 9 in the standard 7-segment display format, and BCD numbers above 9 into unique patterns that verify operation. There you go. All circuits operate off of a single 5-volt supply. The 7447 outputs which withstand 15 volts and a maximum leakage current of 250 microamps. Features: lamp test input, leading trailing zero suppression, RBI and RBO, blanking input that may be used to modulate lamp intensity or inhibit output, TTL and DTL compatible, input clamping diodes. Great. BCD to 7-segment decoder / drivers. Isn't that what we just saw? What's the difference? BCD to 7-segment, BCD to 7-segment. I don't know what the difference is. This versatile series of 7-segment display drivers fulfills a wide variety of requirements for most active high and active low. Probably one is active high and one is active low. Yeah, right. Dual 2-wide 2-input and or invert gate. And or invert. The devices described in this data sheet employ TTL to achieve high speed at moderate power dissipation. They are consolidated into one sheet since they perform and or invert functions with only differing numbers of AND inputs or terms. Characteristics include high noise immunity, low output impedance, good capacitance, drive capability, and minimal variation in switching time with temperature. The gates are compatible with and interchangeable with Series 7.4 devices. So it's AND or invert, AND or invert. And there's the schematic diagram. Okay, then we've got dual JK master slave flip-flop. This is just the TTL equivalent of what we saw earlier. So we've got the JK flip-flop and we've got the dual D flip-flop, 2 D flip-flops. We've got a quad latch. Okay. The latch is ideally suited for use as temporary storage for binary information between processing units and input-output or indicator units. Information present at a data D input is transferred to the Q output when the enable G is high, and the Q output will follow the data input as long as the enable remains high. When the enable goes low, the information that was present at the data input at the time the transition occurred is retained at the Q output until the enable is permitted to go high. The 7475 features complementary Q and Q bar, I don't know how you pronounce that, inverted Q outputs from a 4-bit latch and are available in 16-pin packages. Okay, quad latch. Dual JK master slave flip-flop. I don't know what the difference is here. I don't know. I suppose we could read the thing. This incorporates separate presets, clears, and clocks. Clock pulse controls inputs to master section and also regulates coupling between master and slave sections. Okay. 4-bit magnitude comparator. This 4-bit magnitude comparator performs comparison of straight binary or BCD codes. 3 fully decoded decisions about 2 4-bit words, A, B, are made and are externally available at 3 outputs. The device is fully expandable to any number of bits without external gates. Words of greater length may be compared by connecting comparators in cascade. The A greater than B and B is less, and A is less than B and A equal B outputs of a stage handling less significant bits are connected to the corresponding inputs of the next stage handling more significant bits. The stage handling the least significant bits must have a high level voltage applied to the A equals B input. The cascading paths of the 8-5 are implemented with only a 2-gate level delay to reduce overall comparison times for long words. Quad exclusive OR gate. Okay, so that's quad XOR, very good. Divide by 2/5 BCD counter. This monolithic counter contains 4 master-slave flip-flops and additional gating to provide a divide by 2 counter and a 3-stage binary counter for which the count cycle length is divided by 5. This counter has a gated 0 reset and gated set to 9 inputs for use in BCD's 9 complement applications. To use maximum count length, decade divide by 12 or 4-bit binary, the B input is connected to the QA output. The input count pulses are applied to input A, and the outputs are as desired as described in the appropriate truth table. A symmetrical divide by 10 count can be obtained from the 90 counter by connecting the QD output to the A input and applying the input count to the B input, which gives a divide by 10 square wave at output QA. All right. We've got some typical ratings. We've got a diagram showing how they all cascade. Got some truth tables. Reset count truth table, BCD count sequence, biquinary. So that's 2 lots of 5. All right, now we're up to decade, divide by 12, and binary counter. Okay, this is the 7492. So the general description, this monolithic, hang on a sec. This monolithic counter contains 4 master-slave flip-flops and additional gating to provide a divide by 2 counter and a 3-stage binary counter for which the count cycle length is divide by 6. This counter has a gated 0 reset. To use maximum count length, decade divide by 12 or 4-bit binary, The B input is connected to the QA output. The input count pulses are applied to input A, and the outputs are as described in the appropriate truth table. And we've got our logic diagram. DC triggering from gated low-level active A and high-level active B inputs. Designed for DC triggering from gated low-level active and high-level active B inputs, provides overriding direct clear inputs and controls pulse width. For example, lengthens pulse by re-triggering or shortens by clearing. BCD decimal decoders / drivers. Okay, well, we know about these. Anyway, these BCD to decimal decoders / drivers consist of 8 inverters and 10 4-input NAND gates. The inverters are connected in pairs to make BCD input. Sorry, I had a phone call, and of course it was a spammer. So anyway, I'm back. So yep, this is the same thing. It's got a 4-bit BCD input and then a 10-bit output, which can be used for decimal numbers. Okay, now we've got a multiplexer, a 16-line to 1-line multiplexer. The 74150 multiplexes 16 digital lines to 1 output. A 4-bit code determines the particular one of 16 inputs, which is routed to the output. The data is inverted from input to output. A strobe override places the output in the logical 1 state. Right. Features. Typical propagation delay 10 nanoseconds. Typical power dissipation 225 milliwatts. And we've got some maximum ratings. And then we've got the logic diagram. So you data select with a 4-bit number, and then you share the output with whatever is selected. And there's a strobe here that will just turn everything on. All right, we've got 4-line to 16-line decoder. The 74154 is a TTL monolithic 4-line to 16-line decoder, which allows decoding of a 4-bit binary coded input into one of 16 separate outputs. The device is provided with 2 strobe lines. All right, both of which have to be in the low state in order to perform the decoding function. If either of the strobes is high, all 16 outputs will remain high. The device can be used as a demultiplexer by passing information from one of the strobes, the other being low, to an output selected by the 4-line input addresses. I don't think I'm going to read that clearly. Okay, I'll read it carefully. Okay, so first of all, it's a TTL monolithic 4-line to 16-line decoder, which allows decoding of a 4-bit binary coded input into one of 16 separate outputs. The device is provided with 2 strobe lines, both of which have to be in the low state in order to perform the decoding function. If either of the strobes is high, all 16 outputs will remain high. The device can be used as a demultiplexer by passing information from one of the strobes, the other being low, to an output selected by the 4-line input address. I haven't understood that. Anyway, I'm not gonna hang myself up on it. So, up-down decade counter, the 74192. The 74192 is a TTL up-down decade counter, which is capable of being preset to any number from 0 through 9. A load input controls the asynchronous entry of these numbers and sets all outputs to appropriate state. Counting is performed through 2 clock lines, one controlling the count in the up direction and the other in the down direction. 2 outputs, borrow and carry, are connected to the clock inputs of subsequent counters to provide for counting to numbers greater than 9. The counter is synchronous by itself and semi-synchronous, 2 gate delays between stages when cascaded. Absolute maximum ratings, logic diagram. Alright, synchronous up-down counter with dual clock. Alright, the 74193 is a 4-bit binary counter. That'll give you, 1, 2, 4, 8, so it'll give you 16 bits, 16 values. Synchronous operation is provided by having all flip-flops clocked simultaneously, so that the outputs change together when so instructed by the steering logic. This mode of operation eliminates the output counting spikes normally associated with asynchronous ripple clock counters. The outputs of the 4 master-slave flip-flops are triggered by a low to high level transition of either count clock input. The direction of counting is determined by which count input is pulsed, while the other count input is held high. Okay. All 4 counters are fully programmable. That is, each output may be preset to either level by entering the desired data at the inputs while the load input is low. The output will change independently of the count pulses. This feature allows the counters to be used as modulo and dividers by simply modifying the count length with the preset inputs. A clear input has been provided when taken to a high level, forces all outputs to the low level, independent of the count and load inputs. The clear, count, and load inputs are buffered to lower the drive requirements of clock drivers, etc. required for long words. 4-bit bidirectional universal shift registers. Okay, cool. So this is 4-bit shift register. The 74194 is a bidirectional shift register designed to incorporate virtually all of the features a system designer may want in a shift register. The circuit contains 46 equivalent gates and features parallel inputs, parallel outputs, right shift, left shift, serial inputs, operating mode control inputs, and a direct overriding clear line. The register has 4 distinct modes of operation, namely parallel or broadside load, shift right in the direction QA towards QD, shift left in the direction QD towards QA, inhibit clock, which is do nothing. Synchronous parallel loading is accomplished by applying the 4 bits of data and taking both mode control inputs, S0 and S1, high. The data is loaded into the associated flip-flop and appears at all the outputs after the positive transition of the clock input. During loading, serial data flow is inhibited. Shift shift right is accomplished synchronously with the rising edge of the clock pulse when S0 is high and S1 is low. Serial data for this mode is entered at the shift left serial input. Clocking of the flip-flop is inhibited while both mode control inputs are low. The mode controls should be changed only while the clock input is high. Okay, features: typical power dissipation 195 milliwatts, typical clock frequency 36 megahertz maximum, parallel inputs and outputs, 4 operating modes: synchronous, parallel load, right shift, left shift, do nothing. Positive edge triggered clocking, direct overriding, clear. Okay, so you can clear everything with one bit. There's your logic diagram. Very good. Now what have we got? 40 megahertz presettable decade and binary counters / latches. These high-speed monolithic counters consist of 4 DC coupled master-slave flip-flops which are internally connected to provide either a divide by 2 and a divide by 5 counter. These counters are fully programmable, that is, the outputs may be preset to any state by placing a low on the count/load input and entering the desired data at the data inputs. The outputs will change to agree with the data inputs independent of the state of the clocks. These counters may also be used as 4-bit latches by using the count/load input as the strobe and entering data at the data inputs. The outputs will directly follow the data inputs when the count/load is low, but will remain unchanged when the count/load is high and the clock inputs are inactive. These high-speed counters will accept count frequencies of 0 to 40 megahertz at the clock 1 input and 0 to 20 megahertz at the clock 2 input. During the count operation, transfer of information to the outputs occurs on the negative going edge of the clock pulse. The counters feature a direct clear, which, when taken low, sets the outputs low regardless of the states of the clocks. All inputs are diode clamped to minimize transmission line effects and simplify system design. The circuits are compatible with most TTL and DTL logic families. Typical power dissipation is 150 milliwatts. Features: performs BCD, biquinary and binary counting, fully independent clear output, guaranteed to count at input frequencies from 0 to 40 megahertz. Input clamping diode simplifies system design. We got a logic diagram and a truth tables and a pinout. All right, and then here we've got some special purpose devices. Okay, so these are listed. There's a SCR, silicon controlled rectifier, triac, and diac. There you go. They don't have many offerings in that class. All right, so I think we're through all of our digital logic circuits. Important suggestions on the use and replacement of transistors. You can use various styles and sizes of transistors in any given circuit application, as long as the electrical characteristics of the device are within the required range of operation. Thus, a tab-type device can be used to replace a TO3 or TO66 case device, or a small epoxy-type device can be used in place of a TO5 or other size transistor. Generally speaking, you must observe the following maximum characteristics of a transistor when contemplating substitution or selection: power dissipation, maximum collector current, maximum collector to emitter voltage, maximum collector to base voltage, maximum emitter to base voltage. Also, it is useful to consider the following characteristics for actual circuit operation: gain and frequency limitations. Caution: it may be necessary in some cases to adjust bias values to achieve required operation. With tuned circuits, it is a good practice to check alignment after replacing any transistor. When replacing power transistors, always check driver devices to be sure they are okay. Also check other circuit components to be sure they were not shorted or otherwise defective when the original device failed. If you fail to correct such problems before applying power to the circuit once again, the replacement transistor could easily be permanently damaged. Be sure to use proper heatsink precautions and use silicone grease to reduce the thermal resistance between the case of the transistor and the heatsink. Always observe temperature limitations as specified with transistor ratings. It almost goes without saying, but let us remind you anyway, always observe voltage polarity with all semiconductor devices. And now we've got the cross-reference / substitution listing, which is the big table that's about to follow. So we'll just flip through that. We won't have a close look. Most users of semiconductors realize that it is almost impossible to guarantee absolute equivalence, as in the case of tubes. Thus, the only way to create replacement or cross-reference listings is by carefully evaluating each characteristic of both devices, original transistor, and the possible alternate. That should say alternative. Anyway, not going to fight that battle. This is how the technical staff of Radio Shack went about preparing the following cross-reference / replacement list. Important note, we caution you that in many cases the listed cross-reference Archer device may be different in appearance, size, or mounting style. Thus, before beginning replacement or installation procedures, check to be sure you have enough room for proper mounting. Also, when making substitution or replacements in radio or high-frequency circuitry, it may be necessary to realign tunable circuit elements. This is true even when making exact replacements. Junction capacitances normally vary between devices even from the same production run. Information contained in this guide is based on the latest available data and is believed to be accurate. Every care is being taken to assure technical accuracy. However, Radio Shack does not assume responsibility for any contingencies of the use of this information, nor does Radio Shack assume any responsibility for infringements of patents or other rights of third parties, which may result from its use. When you are looking for a specific number and it does not show up in the following listing, refer to the technical data provided for our line of Archer devices. With this information, you will probably be able to make a suitable substitution. And then here we go. This is the 46,000 Archer Semiconductor Replacement Guide. So on the left-hand side, you've got the device as it's commonly known. And then on the right-hand side, you've got the 276 Archer Semiconductor Replacement code. And these numbers will mean nothing to you unless you... well, some of them. Okay, so they've got the 1 ends and the 2 ends. Okay. Fair enough. That's all different types of diodes, and a 1 end for diode and 2 end for transistor. Very good. So this is what we did before computers. Actually, they made this table with the help of a computer. There is some interesting material at the back of this, so we'll just flip through the tables, which are not useful. I wonder if you can still buy those Archer Semiconductors devices, or if they're... I don't know what happened. Actually, I'll go and see if I can find out. Hang on a sec. All right, so I just went to look up Archer to see what happened to it, and basically it dried up when Radio Shack did, which sort of in the late 90s, when hobbyist market just sort of evaporated. And the Archer line was just a brand. It was a Radio Shack what didn't run their own fabs. So they didn't make circuits. They just rebranded the the components from the major players, and put them in small bags with high markups for selling to hobbyists back in the day, when that was the sort of thing that hobbyists might do. Yeah, it's not the hobby that it used to be. Electronics, it's all changed, and now you can buy a microcontroller and do it all in software. Software continues to eat the world. All right, so now we've got some. We've got case styles. So let's have a close look at those. Let's finish my coffee. All right, so we've got A1. I wonder if these drawings are to scale. They must be. What do you reckon? I don't know. It's A1, A3, D041, M532A, M548, MU27, MU114, T01, T03, T05, T039, T0, or is it TO? Is it 0? Oh, I'm not sure. TO44, TO72, TO92. I think that's probably the one that we tend to use these days. TO92 plus. Okay. TO220. Okay. X55, 277101 and 277103. All right. Those are different sizes of LCD case. All right, and we've got major semiconductor components. So there's the name of the device, the circuit symbol, commonly used junction schematic. Interesting. Electrical characteristics, max ratings available, major applications, roughly analogous to check valve, diode tube, gas diode. Well, this is quite interesting. So we've got diode or rectifier. We've got an avalanche Zener diode. We've got an integrated voltage regulator. We've got a tunnel diode. We've got a back diode, thyrector, NPN transistor, PNP transistor, phototransistor, unijunction transistor, a UJT. Complementary unijunction transistor, CUJT. Programmable unijunction transistor, silicon-controlled rectifier, complementary silicon-controlled rectifier, light-activated SCR, the LA SCR, silicon-controlled switch, silicon unilateral switch, silicon bilateral switch, triac, diac trigger, and that's it. Fascinating. All right, and now we're into the glossary. Wow. The following letter symbols and abbreviations are recommended by the Joint Electron Device Engineering Council, JEDEC, of the Electronic Industries Association, EIA, and the National Electrical Manufacturers Association, NEMA, for use in semiconductor device data sheets and specifications. Wow. There's a fair bit to know, isn't there? A or A for anode, B or B for base. BFS, common source small signal forward transfer susceptance. BIS, common source small signal input subsistence. Right. No, these all look like things that I don't know what they mean. What on earth is susceptance? I don't know. Don't know. So looks like I've got a lot to learn about there, but I won't be learning it from this glossary. There we go, space in the back for our notes. Wonderful. Well, we got through the book. I'll throw the farewell cam. We'll wrap up. And that's a wrap. So we learned a few things today. We learned about the Archer brand of electronics, which was for hobbyists from Radio Shack back in the day. This is the 1978 edition, as we said. We saw the LM amplifiers. We saw the 7.4C logic. We saw the 7.4 logic, and we saw the 4000 series logic as well. So that was pretty cool. Had a little bit of information about things like silicon versus selenium and germanium versus silicon and this sort of thing. So yeah, it was pretty interesting. What was my favorite thing in here? I wonder. I thought that the microprocessor was pretty cool. That was probably the most sophisticated thing that they had in here, the 8080 microprocessor. That was pretty cool. What was the most baffling? I think, what was baffling? Well, I didn't know what how you used the strobe with the multiplexers. That was a bit beyond me. I didn't quite understand that. Some of it was pretty simple. Some of it was surprising to see. Like for instance, static RAM. They had static RAM. I thought some of that might have come later in history, but apparently not. So in 1978, they had static RAMs. Apparently, the Archer brand goes back to the 60s, so they probably had it well in advance of 1978. Anyway, that's the end of this video. I hope you enjoyed this video. Thanks very much for watching, and please remember to hit like and subscribe.